at the end of chapter 15. Work through those, and then we'll do our pre-lab for the activation energy, which we're going to do on Thursday. All right, so the first one, problem number 22, you've got some mastering chemistry problems that are somewhat like this. It says, find and label each mistake in the equilibrium constant expressions. So in A, the equilibrium is that 2HS, or 2H2S, yields 2H2 and S2. And everything's in the gas phase. So it's a homogeneous equilibrium. And it's got the K expression. And as we've been writing Ks, we would call this one as a K sub C because it's in concentrations. So if we look at the expression, it tells us that there's a problem with it, and we need to figure out what the problem would be. What would we need to do to correct this one in A? Need a what now? Okay, for which one? Yeah, so the two that have 2 in front of them need to be squared. So those guys need to have squared in the K expression. Okay, let's look at the similar type of thing with what we would do for B. B says carbon monoxide plus molecular chlorine yields COCl2. All right, so everything's a one stoichiometry. What's wrong with this one? Products and the reactants. So product should be on top, and it's on the bottom on this one. So everything needs to be inverted on this guy. All right, so we want to cross that out and put the products on top and put the reactants on bottom. Okay. All right. So that one's easy enough. Let's look at the next one. So the next one is problem number 24 in the notes. This is kind of a pictorial one, but we have to understand what's going on. It says ethene, C2H4, can be halogenated by reacting with one of the following halogens. Halogen is represented by X2. And the halogens are either going to be molecular chlorine, molecular bromine, or molecular iodide. Okay, so look at the 3 figures below, and it says everything's at the same temperature, and it wants us to rank the equilibrium constants from largest to smallest. So what we have is we'll just represent them with black colors. The one that's got the green in it, this is the one that represents the chlorine. The one with the brown, that doesn't look very brown, but that's the bromine, and the bluish purple represents the molecular iodide. Okay, so if we look at kind of the structure of what's going on with these guys, we're going to count the number of moles of the chlorine. So the chlorine atoms are green. So this would be this reactant that we're going to count on each one of them, versus the number of moles of product. So if we think of this, we've got reactants on this side. Reactants and products on this side. So if we look at what are the reactants are, I got 1, 2, 3, 4, and the others on the other side are the reactants. So it is a 4 reactants to count the moles of product I have. I've got 1, 2, 3, 4, 5, 6, 7, 8. It's 4 to 8 is the ratio of the two. All right, so if I look at the next one and do a similar count, so I'm going to do the similar thing for selecting the reactants. So the reactants 1, 2, 3, 4, and then 5, 6, 7, 8. I've got 8 reactant molecules. All right, and if I count the number of product molecules I have, number of product molecules I have, 1, 2, 3, 4, 5, 6. Okay, so I'm going to do a similar thing for the last one. So the number of reactant molecules, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. It's 14 reactant molecules. The number of product molecules is 1, 2, 3. I guess it's 3. All right, so it wants us to rank now the equilibrium constants from largest to smallest. The larger the value for K means the further the equilibrium lies to the right. It favors products. So which one of these favors products the most? Okay, so the one that's got the most products in it is the chlorine. All right, so that would be the K of the chlorine is going to be the greatest. And then if I look at the one in the middle going from left to right, the middle one would be the bromine. And finally, the one with the fewest moles of products is the one with the most reactants left. That would be the K of the iodine. So we're kind of looking at the picture graphically and figuring out how that relates to the equilibrium constant. The key thing is to recognize which are reactants and which are products, and then you can kind of do a count and inventory of which ones are there, and figure out what's being made in the system. Question on that? All right. Okay, 28 says the equilibrium constant K sub P is a value 2.2 times 10 to the 6 at 298. It gives me the equilibrium. Calculate the K of P for each of the following reactions and predict whether or not the product would be, or the reactant would be favored in equilibrium. So remember that if K is, going back to what we said, K is much, much greater than 1. That means it favors products. If K is much, much less than 1, that means it favors reactants. And if K is close to 1, it's kind of in between. All right, so as written, this reaction for the K sub P is a big number. It's 1 million plus. So it's definitely favoring in the forward direction. All right, so our issue is that while each one of these A, B, and C are related to our equilibrium, it's not quite the same thing. So we have to figure out how to convert the equilibrium we have to the one that's written and find out what the K value would be for it, and then figure out which way it's going to go. So let's start with A. What would we need to do to A to make A equivalent to the one that's up here? Or take the one that's up there and make it equivalent to A, either way. Okay, if we took A by a factor of 2, but A is what we're wanting to know K sub P for, so let's go the other way. So let's take this one. So if we do that one, we need to divide everything by 2. All right, so if we took this K sub P and we took and divided everything by 2, I'm going to write the expression out right quick. And we took and divided everything by 2. So the same as multiplying it by 1/2. The 1/2 of 2, that just makes that the CO, 1/2 CO2, 1/2 CF4. So that's equal to this expression at that point. Okay, so if we multiply everything by 1/2, that means that the Kp new would equal the K original to the 1/2 power. So if I take the square root of 2.2 times 10 to the 6, I'm guessing this off my head, it's somewhere around maybe 1.4, 1.5 times 10 to the 3rd. Gotta get rid of the square root there. And I can measure that or put that in your calculator. But it's pretty close to that. It's still a big number. Okay, so it's a number that's well above 1,000. So that means it favors products. It's a large number. let's look at B then. So on B, I've got 6 where it's 2 here, and I've got 3 and 3. So this one, the K sub P for B, would be the same as the K sub P original times 3 or to the Q power, to the third power. So it would be something to the 18th. All right, so it would be the 2.2 times 10 to the 6th. So it's going to be somewhere around 9 times 10 to the 18th, whatever the math comes out for it. And in the similar fashion, it's highly going to favor products going in the forward direction. All right, so let's look at the last one. Okay, so what's the issue with C? Flip it around, exactly. So on C, what was the reactant is now the product. So I've got to spin it around. So if I take the top one and spin it around, so it becomes CO2 plus CF4 yields 2 COF2s. And if I flip it around, the K is equal to the inverse of the K original, so the inverse of 2.2 times 10 to the 6th. So does that make them equal to each other now? Still not, because this is a 2, this is only a 1. So I need to multiply everything in this by 2. So 2, 2, this becomes a 4. And when I do that, I need to square this term. Okay, so that's something to the minus maybe 13th or 12th. Thirteenth. 2.1 times 10 to the minus 13. Okay, so on this one, this is a number much, much smaller than 1. This one's going to favor the reactant side. Okay. Say again? Why is it 1 over? Okay, because we had to take this one and flip it around. Right, so it's when you spin it around, that's when you have to take the inverse of it. You multiply it by something, you take it to that power.
Yeah.
Yep.
So for B, why subtract?
We're not. So this is K sub P original.
Just all.
Yeah, that's just this number. That's what I'm saying.
Then why is the
It's not the 3 didn't show up with my finger. So that is a 3. So something to the maybe 18th. So what the exact value was. So, yeah, 1.1 times 10 to the 19th. That's off a little bit. That's the actual number. Okay. All right. Problem number 30 says use the reactions in their equilibriums to predict the equilibrium constant for something another reaction. So I've got 2A decomposes to fill our 3A 3Ds. And I've got these 2 reactions that are given, and I've got to figure out somehow to put those 2 things together so that the combination of these, once added together, yield this guy. Okay, so I've got the values for, this one's going to be called 1 because it's K1. This one would be 2. If I look at the number 1, and if I look at the reactants, what's common between number 1 and the reaction I'm trying to solve for this one? What's related between those two things? The A's in there. But how many copies of A do we need? That means I've got to use that one twice. All right, so I'm going to take and rewrite 1 and rewrite it as 2A yields B plus 2C, and its value now is, I'm going to call it K1 prime, is equal to the K1, and I use 2 copies of it, so I'm going to square it. All right, and then if I look at D, our reaction number 2, how's reaction number 2 related to the one I want to solve for? It's got D in it, but it's on the wrong side. So that tells me for the next one, reaction number 2, I'm going to need to at least spin it around. I've got to take this guy and turn it around. So I'm going to rewrite it as B plus 2C yields 3D. So the K prime number 2 is just the inverse of whatever K2 was. So 2.35. So whenever you spin it around, flip sides, you invert the value of K. Now, if I were to take those two things and add them together, I can see that there's some common things to both sides. There's got a B on the left and a B on the right, and they cancel out. I've got a 2C on the left, a 2C on the right, and they cancel out. So what I have left when I put those two equilibriums together is 2A yields 3D. That's what I'm looking for. So the K value for it is just the product of these two K's multiplied together. So it would equal to the K prime 1 times the K prime 2, which would just be the 0.0334 squared divided by 0.235. And I get, I guess this is 4.92 times 10 to the minus 6. Did I get that? I got it again. No, Tuesday. Didn't that time, so I put something in wrong. How about 4.7 times 10 to the minus 4?
Yes. Yeah, that's fine.
Yeah. So I entered something in the calculator. Okay, so you'll have a question like this on the exam. You've got a question like this on the Mastering Chemistry. You're given some equilibrium information, a K1 and a K2. What makes it complicated sometimes is you're given 5 Ks. And you may got to choose 2 to put together, or you may need to put 3 together. But you got to figure out how to rearrange these to get the K value that you want. So if we want to make it trickier, we put a bunch of Ks in there that you don't even need to use at all. You got to critically think about what's needed and what's not. Key thing to approach it is you look at what are my products and what are my reactants. Are they in my reaction? If they're there, and I know this is the only place there's A, I know I've got to use this one. And if this is the only place of D, I know I've got to use this one. Now, if I had other equilibriums that had A and D there, now I've got to make choices. But with those, I didn't have a choice. It's the only source of. Okay? Okay, so 32, I've got K sub C values given for a couple of equilibriums. and I need to know what is the K sub P, or it wants me to do the K sub P. And at the bottom of the page, I've got the K sub P expression. So K sub P is equal to K sub C times RT delta N. I know the temperature. All these are at 298 Kelvin. I know the KC values. The only thing I need to do is calculate what delta N is and plug it in and crank them out. Okay, so let's assign the delta N for all of them, and then we'll work one of them. All right, so if I look at delta N is the number of moles of products minus reactants of gas. So on this one, I've got 2 minus 1. It would be a positive 1 for A. If I look at delta N for B, it's 2 minus 1 plus 3, which is 4. It'd be a minus 2 for B. If I look what it would be for C, it's 2 minus 1 plus 1, which is 2, so delta N is 0. Now this would be the simplest one to do. So for number C, the K sub P for number C, when I throw that into the equation, K sub C is equal to RT raised to the delta N power, but delta N is 0. That means this term drops out and becomes 1. K sub C equals K sub P in this case. So this term just equals the K sub P. If it's something other than 0, we've got to plug it in. So let's do B. So the K sub P for B. Let's do this one. All right. So the K sub C value is 3.7 times 10 to the 8. Right, and then we've got to multiply that times R. The gas constant is 0.08206, and then times the temperature. The temperature is 298, and then raise it to the -2 power. So play along with your calculator. See what you get. And I got 6.2 times 10 to the 5th. So on my calculator, once I multiplied these two things together and got a number, so whatever that number was, I took and hit the Y to the X button and put in -2. And then hit equals, and that took that to that power, and then I multiplied that by the value of K sub C. So you have to figure out how to do it on the calculator. Question on that? Good. Okay. Let's look at the next one. All right, so 34 says find the mistake and fix. So this is somewhat like we did in the earlier ones. This one's different in that it involves some different phases. Okay, so what we see in this one is that we've got a gas and a pure liquid. And if you remember what we said, if things are in the pure liquid state or they're in the solid, then they appear, or they're not in the K expression.
But if they're aqueous, they are?
If they're aqueous, they are. That's correct. All right. Or if they're gases, they are. Okay, so if something is just, if it doesn't represent its phase, okay, or it doesn't, if it's aqueous, Sometimes we get lazy and don't write something that is in water, like HCl, when we know it is in water, because HCl is a gas at room temperature. And we're talking about a solution of it. We get lazy and not write that, but in reality, it's aqueous. And I'll try to write that on all the test questions. If it's unclear to you on the test question, ask it. I'll clarify that to the class because I just missed it then. All right, so our problem is the one that's the in the liquid state. It doesn't appear in the expression, so we simply need to take it out. K sub C would be products, the chlorine, divided by the PCl5. So we'll remove that 1, and that's what's left. Okay, that one's not bad. All right, so 36 says you've got this reaction that occurs. You've got a solid, and it produces 2 gases. And it says an equilibrium mixture at a certain temperature has a certain concentration of ammonia, which is one of the reactants, or one of the products, and it has a certain concentration of hydrogen disulfide, which is also one of the products. And it wants to know what the value is of K sub C at this temperature. So we're looking for K sub C. That's the question mark. All right. Now we don't know anything about the concentration of this reactant. Does that matter? No, because it's in the solid. So if we write the K sub C and its products over reactants, it's the concentration of the NH3 divided by times the concentration of the H2S. So that would be the product side of it. And the reactants are just over 1. So we can just drop 1 off. So it simply becomes the concentration of the ammonia, NH3, times the concentration of the H2S. And multiply those together. Three sig figs. 0.0987. Okay. So we know everything in it. We just have to plug in, crank out. All right. 38 is a little bit more. Need some more information on this one. So on this one, it's a homogeneous. Everything's in one phase. So H2 plus I2 yields 2HI. If I write the K expression, so K sub C is going to be the concentration of the products divided by the concentration of the reactants. All right, so is that the K sub C expression? What did I miss? Got to, because of the 2 stoichiometry, got to square that one. Square that one exactly right. Okay, so I got to fill in all the blanks, or I need to fill in all the blanks. It tells me that the concentrations are given are molar concentrations, so I've got all of those. So on the first one, I'm trying to find out what is K sub C. So on this one, I know what the concentration of all the reactants are, as well as the product. I just simply plug them into the equation and crank it out. So I've got 0.922, square that, divided by the reactants, 0.0355 times 0.0388. And whatever that number comes out to, that's going to be what K is. And I get 617. Okay. All right, so that's how we approach A. On B, the temperature has changed, and it tells us, it wants us to know what K sub C is. Did anybody else get 617? Yeah. Okay. All right. B, the temperature has changed, and there's a different value of K now. what we want to know is, given the concentration of this reactant and the product, what is the concentration of the H2? So now we know this term, and this term. We need to rearrange it to solve for what is the H2. So I'm just going to cross multiply. And when I cross multiply, I'm just going to switch places with the H2 in the K sub C. So this one went up here, this one went down here. Now I know all the terms that plug into that. The concentration of the HI is 0.387. Got to square it. The value of K sub C is 9.6. The concentration of the I2 is 0.0455. I got 0.343 moles. Okay. All right, let's go ahead and do the part C while we're just doing it. All right, part C, it's changed that we know the concentration of both of the reactants, and we know the concentration of K sub C. What we don't know on this one is we don't know what is the value of the HI. So that's what we're looking for in this one. So now when I rearrange this equation, I've got to isolate this term out of it. So I'm going to cross multiply these two terms over the other side. So do that first. So that says that, that the concentration of HI squared is equal to K sub C times the concentration of H2 times the concentration of I2. Okay, but I don't want HI squared, I want HI. So how would I get rid of the squared? Square root of both sides. So if I take the square root of both sides, the square root of HI squared is just equal to the concentration of HI. So now I just need to plug the numbers in on the right-hand side. So K sub C is 50.2. The concentration of the hydrogen is 0.0485. Concentration of the I2 is 0.0468. Just multiply all those together. Then take the square root of it, and I get the concentration of the HI 0.338. I want to round up. Anybody else get that? Yeah. So you'll likely have a problem like this. You're either going to be given all the concentrations and you have to calculate K sub C, or you're going to be given K sub C and all the concentrations but one, and then you're going to have to calculate concentration of that. The key thing is that this is, if it's at equilibrium, everything's already adjusted and we can go directly to the ice table or plug it in the K sub C. If it's not at equilibrium, which is what we're talking about in class right now, we've got to let it go to equilibrium first, and then we've got to solve for it. That's what we have to do with the ice, and that's a much more complicated problem. We're going to do some of those in just a second. And so recognize the easy ones and be able to do those. Okay, so problem number 40 says we've got a reaction, we've got a K sub P. It gives me the partial pressures of two of the reactants in torr. or two of the products. So I've got, this is a product in the system, and this is a product. All right, so I know what K sub P is. What I want to know is what is the partial pressure of this component. All right, so this is kind of like what we did with the previous problem. The only issue is that when we solve partial pressures, we need the units of pressure to be in what? Atmospheres. So we've got to take these torrs and get them in atmospheres. So 1 atmosphere is equal to 760 torr, and a torr is equivalent to a millimeter of mercury. So 760 millimeters of mercury. So we need to take each one of these values in torrs and divide them by 760 is what it comes down. So 137 divided by 760. So this is 0.180 atmospheres. And 285 divided by 760. 0.0375 atmospheres. So now I need to set up the K sub P expression and solve for the unknown. So K sub P is the partial pressures of the gases raised to the respective powers divided by the partial pressures of the reactants. So the products are the partial pressure of SO2 times the partial pressure of the Cl2 divided by the partial pressure of the S2O Cl2. S2O2 Cl2. All right, so on this one, this is the one I'm looking for. I know the pressures of the other two products. I know the K sub P, so it's just a rearrangement that needs to occur. I know all these things. Just plug it in. So and I get a really small number. I get 2.32 times 10 to the minus, and their units are atmospheres, to the minus 5th atmospheres. If I wanted that back in torr, I could multiply it by 760, and it would still be a small number. It's not as small as the atmospheres. Okay, let's think about, does that make sense? So these were around 0.1 and 0.3, so 0.2 and 0.4 maybe. So that's these pressures. So why would it make sense that this one is so small? If this guy's 10 to the minus 5th, why would that make sense? K says high. Products are favored. The reaction, because this value is 1,000 plus, this reaction wants to run in that direction. That's kind of a check you can do to make sure you get an answer that makes sense. If the K would have been very small, 10 to the minus 3, I'd expect this number to be big compared to the others. Okay, so this is just kind of a mental check that you can look at, make sure that you're setting the problem up, getting a reason idea of it. Question on that one? Yep.
So if there would have been coefficients where we had to
Take them to the powers. Yeah. So if this had been a 2 and a 3, we'd have to take it to a 2 and a 3. Absolutely. Pressures, K sub P's work exactly like K sub C's. The only difference is you use a partial pressure instead of molar concentration. Everything else is the same. Yes.
It's kind of like a little question. You know how you're supposed to the equilibrium mixtures, in this case, take the gases and aqueous solutions.
Yes.
is there like, do we do it for when?
Okay, so if this had been a case of P and this had been a solid, is that what you're asking?
Yeah.
Okay, if it had been a solid, this term would completely drop out. Case of P would just been these two things.
So then is there a time where doing solids or no?
Never. Yeah. Solids and pure liquids are never.
That's
Yep. Anything else? Okay. So 42. This one's a little more challenging. Yeah, I guess it is. It tells us that you've got a reaction 2A plus, or 2A decomposes to yield B plus 2C. And it tells us the reaction initially only contains A. So there's some of this guy, and there's 0 of these to start with. And then it tells me the pressure of A is 235 initially. And then once it reaches equilibrium, the pressure of A drops to 55. And I want to now calculate what is case of P. So this is an ice. I've got initial and I've got an equilibrium concentration. That's the approach I've got to use. So I'm going to write my reaction out. And initial, change, and equilibrium. Okay. To do case of P's, we need to be in atmospheres. So you could work all this out in millimeters of mercury and then convert it to atmospheres to solve the case of P. I choose to just go ahead and put it in atmospheres to start with. So whenever you're doing a case of P, you just got to think everything goes to atmospheres. So pressure in atmospheres. So I'm going to take these two and convert them to atmospheres. So 255 divided by 760 is 0.336, and 55 divided by 760 is 0.072. Okay, so I know initially the pressure of A is 0.336 atmospheres, and I know at equilibrium it ends up at this number, 0.072 atmospheres. Okay, so now if I look at the change that's going to occur on these, the way that I tell you we ought to look at the changes is the one that's a single copy of something, call it X. All right, so this reaction has but only one choice in a direction to go, because initially there's no products, there's only reactants, got to go forwards. So that means this is going to increase by X plus X. There's 2 of this one, it's going to increase by 2X. These are at 0 and 0. And then this one is a 2, but it's a reactant, so it's a minus 2X. So I can take the information that's in the first column, I can take this one and I can find out what the value of X is. Okay, so let's take and figure that out. We know that 0.336 minus 2X is equal to 0.072. Okay, so we're just going to take and solve for what X is. So subtract the 0.072 from this side. That gets it over here. And then add the 2X to both sides. So equals 2X. So 0.336 minus 0.072. And I get it's 0.264 is equal to 2X. So divided by 2, X is equal to 0.132 atmospheres. Okay, so now that I know that piece of information, I can go back and plug in to what B is. B was 0, it increased by the value of X. This is the value of X, so its equilibrium concentration or pressure is 0.132 atmospheres. This one was 0. It increased by 2x. 2x we just said was 0.264 atmospheres. Now I know the equilibrium pressures of all the species. K sub P is products over reactants raised to the respective powers. So the partial pressure of B times the partial pressure of C squared because of the 2 divided by the partial pressure of A square on it because of the 2 stoichiometry. So I know all these numbers. We just plug them in. So the partial pressure of B is 0.132. Partial pressure of C is 0.264. We've got to square that one. Divided by the partial pressure of A, 0.072. And this one was squared. Let the square off of it. I got 1.77. Somebody else tell me if they got that. You got 0.127? All right, let me do it again. Yeah, I got that again. I think that's a good number. Remember to square both the term for A and C. Yes.
So is it a negative 2x because it's on the reactant side?
Well, it was over here, but when we changed this to the other side, it became positive.
For the change.
So this was a negative. So we subtracted this from this. So when we set this up, we took count that it is negative. But these are all going to be positive because they're reactions going in the forward direction. Okay. And if we run into one, we don't know if it's negative or positive. We write it out one way, and it may come out that when we solve for x, x comes up to a negative number. That's absolutely possible. It corrects itself. So if we're not for sure, is the reaction going in the forward or reverse direction, and we don't solve for Q, you could always, if you have the information, solve for Q, like we talked about. We'll do some of those in a second, and then plug in and find out which way it's going. But if you don't have the information to do that, you just take a guess and you call it. In this case, we're saying it's going forward, so the reactants are going down, being negative. Products are being formed, they're going to go positive. Okay.
You have to assume which way the reaction is going. You end up with a negative value as equals. The right answer is negative. You have to redo it.
It won't. No, you don't have to redo it. It would just come in the math that if I would said this is positive and this is negative and negative, when I came up with the value for x, the x would be a negative number. It would have still came up to the exact same value when you solve the math at the end. Okay, here's another one like this. So I've got a equilibrium given. The reaction initially only contains some of the reactant. So I've got some of this stuff in here at 0.02 molar. At equilibrium, I know the concentration of chlorine. So initially I had this amount. Then at equilibrium, I've got this. And I want to know what the value of K sub C is. So we need to recognize this is an ice problem. So start with writing the reaction out. Okay. What do I know? I know initially this concentration is 0.02. There was none of the other reactants. And I know once this reaches equilibrium, the concentration of the chlorine is 0.012 molar. Okay, so this is where I needed to define which way the reaction is going to go. So it says it's initially made of only the reactant, so that means it's got no choice. It's got to go. So everything here is a one-to-one stoichiometry, so that makes this one pretty simple. This is a minus X, this one's going to be a plus X, and this one's going to be a plus X. It went from 0 to 0.012. That tells me that X is equal to 0.012. So that means I know the concentrations of the other product is 0.012, and I know how much of the reactants left over. It's the initial amount less X, so 0.008 is going to be left. Okay, so now I know those. It's just a matter of plugging in K sub C, products over reactants. Nothing's raised to a power because it's all one stoichiometries. I got K sub C is 0.018. Okay. Now, does that make any sense to me? That's that value. So it's about 100th ballparking. And if I look at what happened to most of the product, more of the reactant went into forming products than there was a reactant. And this one, there's 2 moles of this one for every one of this one. So, yeah, that makes sense that this number is going to be substantially less than 1. So, yeah, that makes sense to me. Yes?
So why are the moles for the
Okay, because it's every time the reaction goes forwards and makes one of these, it also has to make one of these. So if this reaction goes forward and it makes X amount of this, it's also making X amount of this one. And it's losing X amount of this one. That's what this column that represents the change, that's what we're defining in that. So if everything is a one-to-one-to-one stoichiometry, it's the simplest case. That's the one you want to see. It's when they're not one-to-one-to-one that you got to think harder about. Okay. All right. So we got a reaction that's got some gas in it, and it initially contains all 3 substances. And I want to know, is it equilibrium? If not, which way is it going to go? So it gives me the pressures and atmospheres. It gives me the K sub P value. So this is going to be an example where we have to solve for Q, and we need to compare Q to K sub P. So this is a find Q problem. Find Q. So Q is written the same way as the K sub P's. So it's going to be products over reactants. So if we write what Q sub P would be, it would be the partial pressure of the H2 squared times the partial pressure of the S2 divided by the partial pressure of the H2S, and square it. The squares are because of the 2's. All right, I know all of those partial pressures. I'll just plug them in. So for the H2, it's 0.112 squared times the S2 is 0.055, and then divided by the reactant, the H2S, 0.445, and I've got to square that one, and we come up with a value for Q. And I get a small number, 0.00348. So in this case, my value of Q I'm doing comparison of Q versus K. And the value for K sub P is 4.24 times 10 to the minus 4. And if I look at the value for Q, it's 3.48 times 10 to the minus third. Okay, so now I've got that. What does it tell me? So which one's the largest? Q or K? Q's the largest. So if Q's the largest, which way does the reaction go? Okay, so Q's larger than K, the reaction is going to run in the reverse direction. If K's the largest, it's going to go in the forward direction. K is going to increase till it gets to Q equals K. But when Q's the largest of the term, it's got to go in the reverse direction. So that was one of the last things that we talked about in class yesterday. Question now. Okay, might have one more like that. Okay, this is a similar problem. The only thing that's different with this one is it tells us the size of the container, and it tells us the moles of each one of the reactant and the product that are in it, and it wants to know in which direction it's going to go, if it's at equilibrium. Okay, so this is a kind of a lot of pieces put together problem, and here's the challenge. If I know the volume and I know the number of moles, what can I calculate? I can calculate the molar concentration, right? But what K is given to me? K sub C or K sub P? K sub P. So what I'm going to have to do is take and calculate a Q sub C based on the concentrations I've got, and then I've got to take that K sub P and convert it to a K sub C so I can calculate Q and K on the equal basis. So this is tricky. Okay, so if I look at, first thing I want to do is I want to find out what K sub C is. So I need to know what delta N is. So delta N is products minus reactants. So 1 minus 2, it's going to be a minus 1. All right, so here's my equation. I know what K sub P is. All right, I'm looking for this term. I know the temperature. I now know what delta N is, R is. So that means that K sub C is equal to K sub P divided by RT to the delta N. So 6.7 divided by the value of R times temperature, 298, and raise that to the minus 1 power. And I get 164. See if somebody else got that. Anyone else get that term? 164. Okay. Now I want to find out what is the molar concentration of the reactant. So the molar concentration of the NO2 is equal to the number of moles divided by the volume, 2.25 liters. It's going to give me molarity. And do the same thing for the product. It's going to give me its molarity. So now I want to plug in and find out what Q is. Q is going to be products over reactants. And because of the 2, got to square that one. And I get Q is 61.2. So Q is 61.2. We found that K was 164. What we see is that K is the larger term. So if K is larger than Q, the reaction has to go in the forward direction. It's going to make more of the product. So this value is going to increase. This one's going to go down. That's going to increase the value of Q until Q is equal to K. That one was tricky on 2 parts. Number one, you had to get it in terms of molar concentration. Secondly, it gave you K sub P, you needed K sub C, so you had to find that one. So that's, is it unreasonable? No, there's nothing on there we hadn't talked about, but you got to think about all the pieces together. That's where the critical thinking comes into play. All right, question on that? All right, so this is where we're going to pick up on, this is where we're talking about, the next problem is where we are in the notes. So you're just starting with something on this one, 52, and how do we solve it when we're just given the initial concentrations in K, and we haven't talked about how to accomplish that yet. So that's going to be the end of what we've got there. There are 18 problems in this Master in Chemistry assignment. It's at least 10 of them, maybe 12 of them, or stuff that we've already talked about. So you can get a good start on this. I encourage you to get a jump on it. Figure these guys out.